we are very eager to hear your talk, and the stage is yours.
Yeah, thank you very much for this kind introduction and also for the invitation here and for your interest in this talk. I have to excuse that for those who are a little bit familiar with this topic, most of my presentation is in some sense really like a colloquium. It's try to simplify things and not with the most recent results and so on. And in the beginning, I will be really very elementary for those who are a little bit in this field. I hope they are not bored. Okay, there are some titles: analysis, geometry, and stochastics. Actually, I'm originally not trained as a geometer, but the main topic of my today's presentation is geometry. How can we understand syntactic geometry or geometric in a synthetic way? And I already gave this brief introduction to students, and let me summarize a little bit the message which I try to give. So the key technique in differential geometry is, of course, differentiation. And but there are plenty of crucial insights which are not related to differentiation. And so conclusions from local to global, estimates in terms of whatever curvature concepts. And one of the interesting things is to put hands on the crucial properties which are related to different notions of curvature. And okay, but before I start with that brief summary, so I first speak a little bit on sectional curvature, comparison geometry, and Alexander spaces. Then I try to motivate that we should not stay with sectional curvature, but pass to Ricci curvature. And then I tell you a little bit on optimal transport, and then we pass to synthetic Ricci bounds. Very elementary beginning. If we are on a singular space, and maybe I should say this, the focus will be to develop this geometric concept for spaces which have minimal irregularity. Like the surface of this room, and you see here points where you don't have differentiability. This kind of singularity is without problem. Here you see if there is a defect of curvature, and things like that we want to include in our setting. And the basic concept is, first of all, a metric space. And so this means, first of all, we have to specify a function which measures distances. And at the end of the day, we want to reduce everything to measuring distances and volumes, measure and metric. And to start with, we measure distances. So this is a function on the product space with values in the real numbers, and it satisfies the triangle inequality. I think this is certainly well known to everyone. And so the distance from x to z is always dominated by the sum of distances if you go via another point. So if I go from here, from Bonn to Dortmund, then the distance is smaller than the distance from Bonn to Munich and Munich-Dortmund. And then we immediately can pass to this concept of geodesic. A continuous curve is called a geodesic if on this curve the triangle inequality is an equality. Yeah, so going from here to there is not more expensive than going from here to there and then from the point in between to the next point. This is the definition of a geodesic. Very easy. Mostly we assume that geodesics are parameterized by arc length, so we speak of constant speed geodesics. So this is hidden a little bit, but should not be stressed too much. And then we directly can characterize what is sectional curvature in Riemannian geometry and what is Alexander geometry in more general setting. So if we have a metric space, we can say that this metric space has non-negative curvature if the triangles look fat. What does this mean? You look on a triangle with vertices A, B, C, and you reconstruct a triangle with the same edge lengths in Euclidean space. And in Euclidean space, then you can calculate the distance from A to the midpoint of this side. And if in your triangle this distance is larger than the formula which you obtain from Euclidean calculation, you say your space is has non-negative curvature, or if triangles are fat. Yeah, in Euclidean space, there is a well-defined formula which allows you to calculate this distance if you know the distances of these sides. And similarly, you say your space has non-positive curvature if the triangles are thin, so the opposite point is closer than you would expect. Triangles have a tendency, like in hyperbolic space, all the triangles seem to touch themselves at a kind of midpoint. And these are more the triangles you would observe if you make triangles on the sphere. And why are we interested in these spaces? This is not only that we have in mind three-dimensional or four-dimensional Riemann manifolds. The idea is that this synthetic concept carry over to infinite-dimensional spaces, to whatever classes of spaces. And I summarize here just some examples to convince you, or to convince perhaps is too much, to invite you to believe that these curvature concepts play an important role in many areas of mathematics. So Riemann manifolds with sectional curvature, non-negative or non-positive, are of course then Alexandrov spaces with these curvature bounds. Hilbert spaces satisfy both of these curvature bounds in this synthetic way. If you have curvature bounds in this synthetic way, then also the Gromov-Hausdorff limits, I will come to this object in a minute. The products of spaces, cones, suspensions, quotients will have similar curvature bounds. What is a cone, for instance? If you have a space X, you construct the product R plus cross X. So X is then something like the unit sphere in your space. And the metric on this cone is given by this formula, where you think that X and Y are points in the unit sphere, and the distance in the cone is given by this formula. And abstractly, this is the definition of a metric in the cone. And so you have explicit formulas how the curvature of an underlying space implies curvature on the cone. Spaces of non-negative or of non-positive curvature are trees, just branching of edges. So just to convince you that we use the same picture, the same notation, that we have the same picture in mind. So this is a tree which has a lot of branch points. This is a typical space of non-positive curvature. Higher dimensional versions of this are Pruha-Titz buildings. Spaces of positive self-adjoint operators in a given Hilbert spaces, or spaces of self-adjoint matrices of given rank, have a metric of non-positive curvature. Spaces of maps, L2 spaces of maps, have the same curvature as the target space, curvature bound as the target space. Yeah, so you define just this distance for maps by integrating the distance of these points. And then the curvature bound for the target space carries over to the space of maps. The Wasserstein space of probability measures on Euclidean space, let's say, or related to that, the space of configurations of a sum of Dirac masses on Euclidean space is a space of non-negative curvature. So what is the space? What is the distance function of the space of configuration? You have a number of points sitting in the points xi and a number of Diracs in yi or yj, and you want to transport the mass from the xi to the yj. What can you do? You can bring, of course, x1 to y1, x2 to y2, and so forth. But you can do better. You can make a permutation of the indices and the y variables, and you take the infimum over permutation and look on this L2 distance and summation. This is the Kantorowicz-Wasserstein distance in this discrete version, and this gives a metric of non-negative curvature. Why is this non-negative curvature for experts? Because this is a quotient. It's a quotient of a flat space. The permutation is a kind of quotient, and without the quotient, it would be a flat space because it's a L2, and then you take a quotient, so you have non-negative curvature. And the same applies to the space of all metric measure spaces. If you have two metric measure spaces, so if these are triples of a space, a distance function, and a measure, and you define a distance by saying it's the L2 distance between the distances, regarding them as function of a product space, and integrating out all variables with twice application of a so-called coupling. This is not thought now to be understood by non-experts. I will come to technical details later on with much slower access. But just to indicate that these kind of objects which play an important role also in data spaces have curvature bounds. And again, the argument is without this infimum, it would be a flat space, it would be a L2 space. With the infimum, it is a quotient, so it is a non-negatively curved space. This is a very simple argument, just from elementary geometric considerations. But we do not only have curvature 0 and as upper or lower bound, we can extend this, of course, to curvature bound kappa, where kappa is a positive or a negative number. And then we compare our given space with model spaces. So, of course, previously we compared with triangles in Euclidean space. If we want to compare, if we want to say a space has curvature larger than 1 or less than 1, we compare it with a unit sphere, which is our standard space of curvature 1, or sphere of radius 1 over square root of kappa. And we take the hyperbolic space if we want to characterize curvature negative 1. Here's one model for the hyperbolic space. You can realize it in the unit ball with this distance function. Yeah, that's not really that much of relevance. You should remember that the sphere has positive curvature just by convention. You have to give a sign to something, and okay, sphere is +1, hyperbolic space is -1 concerning curvature. And our definition now is as before, still the same picture, but now this should be the triangle on the space of model space of curvature kappa, sphere or hyperbolic space or Euclidean space, and we say the triangle is fatter, or we have curvature larger than kappa if we are in this situation, if these distances are longer than expected, and we say curvature is less than kappa if the distances are shorter than expected. So this is very easy concept of curvature. And what are typical results which you can prove in Alexandrov geometry? You have this local to global result. If you verify this fatness of triangles for all small triangles, each point has an epsilon such that in the epsilon neighborhood you can verify that, then all triangles are fat. Yeah, then huge triangles are also fat. And Bonny-Myers, if the curvature is larger than kappa, then your space cannot be too big. Because then after, if kappa is 1, then the diameter is less than pi. You will come back to your point. And these are typical results which do not only hold in Riemannian geometry, but whenever you have these synthetic curvatures. Now, this was Alexandrov geometry developed in the 50s of the last century. Okay, I should add 2 more results. Then this was complemented in some sense by notions of Gromov, who applied the so-called Gromov-Hausdorff convergence. So it's a notion of distance between metric spaces. Yeah, you probably know the Hausdorff distance between metric spaces, and Gromov-Hausdorff space means it's the infimum of a Hausdorff distance whenever you embed the 2 spaces in an ambient space. You have a metric space here, a metric space there. You put them into one big space, and then in this big space, the best embedding and the minimal Hausdorff distance. This is Gromov-Hausdorff. And this Gromov-Hausdorff fits perfectly to this concept of Alexandrov. Namely, these curvature bounds are stable under Gromov-Hausdorff convergence. And even more fascinating, if you impose a curvature bound from below, a dimension bound from above, and a diameter bound, then this is compact. Yeah? If you have these 3 numbers, k, n, and l, then this is compact. Whenever you choose a sequence in this space, you have a limit. And if you choose a sequence of C-infinity spaces, the limit at least exists as a metric space. One accumulation point, not necessarily unique limit. It exists, and of course, if you stay within the class of Riemann manifolds, this is never compact. That's clear. You can approximate the surface of this lecture hall by the infinity manifolds, but the limit is not the infinity. It's not smooth. It's like Sobolev spaces. Yeah? If you think of W1, 2, you can approximate this with the infinity function, and you always can approximate everything with the infinity. But in some sense, it's nice that you can work with Sobolev functions without referring to approximating sequences. And that's the same here. You do not want to refer to approximating sequences of Alexandrov space. You simply say, okay, I have this metric space, and this is a perfect object of research in its own. Sometimes there's an approximating sequence, sometimes not. Doesn't matter. Whenever these curvature bounds are satisfied, I can make this and that conclusions. Okay, there is also an analysis on these spaces. I will omit that because we will see that this is part of a larger class. And indeed, the larger class has to do with the fact that in analysis and probability, it's not the sectional curvature, which is the crucial quantity. It's for most results for Ricci curvature. So for most analytic and results in stochastic analysis, it's the lower bound on the Ricci curvature. Also for upper bound on Ricci curvature never shows up. It's always the lower bound on Ricci curvature. It started with works of S.T. Yao and Chiga, but also with probabilists, Ellsworth, Malima, Bismuth, and then of course with a fundamental work of Perelman on Poincaré conjecture. It was again pushed in the focus of general audience. What is the Ricci curvature? The Ricci curvature is the mean value of sectional curvature. So in naive terms, sectional curvature requires two parameters. If you have two basis vectors in your tangent space, EI and EJ, these two vectors span a plane, and you calculate the curvature in this plane, whether this plane looks more like a sphere or more like a hyperbolic space, this two-dimensional subspace. This is the section curvature. And now Ricci curvature, you fix one direction and take all n-1 directions orthogonal to it and sum up the section curvatures. So it's the mean value of all section curvatures which have one direction in common. And of course, Ricci non-negative would allow that section curvature could be quite singular. And we have examples where section curvature decays like negative 1 over r squared and increases like plus 1 over r squared, and Ricci is still non-negative. So there are a lot of model spaces where section curvature is not preserved. Okay, why is Ricci curvature of interest? Let me list here some typical properties of spaces which have non-negative Ricci curvature, just to make things simpler. And the philosophy is that spaces which have non-negative Ricci curvature have heat flow and optimal transports which behave as nicely as an Euclidean space, in many respects. Of course, not in all. So you have heat kernel comparison. The heat kernel on these spaces is pointwise bounded below without any additional constant by the Euclidean heat kernel. By the formula for the Euclidean heat kernel here with a distance function, of course. You have a Liao estimates, they are a little bit more complicated, they would require a separate slide. You have gradient estimates that the gradient of a heat flow is dominated by the heat flow of a gradient. You have transport estimate. If you start two heat evolutions and measure the Kantorowicz-Wasserstein distance, then this does not increase. And on a more refined level, it also means whenever you have 2 points, you can start a coupled pair of Brownian motion, starting in these 2 points, such that pathwise the distance never increases. So this is really rather remarkable. Each of them is a Brownian motion, and they move around and never increase the distance. If you try to do that with your partner, I think it's quite challenging to do that in a non-Euclidean framework. And each of these properties is sufficient and necessary for non-negative Ricci curvature. And therefore, of course, in the previous second half of the last century, people could thought about what is a synthetic definition of non-negative Ricci curvature. You could pick up any of these conditions and make it to a definition. And actually, in applied sciences, these properties are very important as a characterization of non-negative Ricci curvature. So for financial markets, for instance, this is absolutely crucial. Yeah? If you vary a little bit your initial data, does your wealth in 1 year vary the same minimal amount, or does it really go like on hyperbolic space? And therefore, Ricci curvature also is an important concept in modeling of financial markets, also of bacterial growth and so on. And of course, you can think also of applying this to discrete spaces. Just replacing Brownian motion by random walk and saying step by step, my random walk, coupled random walk should not increase distances. And this is then the concept of a Ricci curvature for discrete spaces, which also plays a very important role. Okay, back to the development of this challenge to find the right notion in the Riemannian setting. So Gromov already observed that in this compactness result for section curvature bound, you also can replace sectional by Ricci curvature bounds. So that it's a much weaker condition. Previously, we had constraint on section curvature, diameter, and dimension. Now we replace the section curvature constraint by a Ricci curvature constraint, which allows much more flexibility. But then, of course, it's just a pre-compactness result, because we are no longer in the metric space setting. We don't have a compactness, or we did not have a compactness for many decades. And therefore, Chige and Colding started to study in detail what is called Ricci limits. So these are sequences of smooth Ricci manifolds with the same uniform lower bound on the Ricci curvature. And as I mentioned, this is a little bit like not going to Sobolev spaces, but studying sequences of C infinity functions which have uniform bounds in Sobolev norm. And but this was a very deep analysis, and Gromov already indicated in, that the right object to consider if one wants to study synthetic definition of Ricci curvature, a space, a metric as before, and now in addition a Borel measure, which should replace the volume measure, the Hausdorff measure. It's not necessarily the Hausdorff measure of a distance. It's another ingredient. And the name of the game is then to find a synthetic notion for these triples, XDM, which is equivalent to the Ricci bound if we are in the Riemannian setting, which is stable under an appropriate notion of convergence. There is also this notion of measured Hausdorff convergence, which is intrinsic or synthetic, which means not referring to approximating sequences, but just using the objects by themselves, and of course, which should reproduce most of the nice results which we find in textbooks of geometric analysis, and which are valid under Ricci curvature bounds. And this is the concept which had been developed by Lott, Villani, and myself in two independent approaches, but very similar approaches, which then is called curvature-dimension condition, CDKN, and which should be regarded as a synthetic formulation of lower bound for the Ricci curvature and upper bound for the dimension. And this is based on this concept of optimal transport, which had been developed in the 15 years before by Fies and many other people, which really gave a big push to this whole development. Let me therefore briefly go a little bit with this idea of optimal transport. So this is now an excursion. It's not necessarily requested for the details of forthcoming chapters. So the concept of optimal transport started with a problem of Morse. Morse raised the problem, if you have two probability measures, mu and nu, you want to minimize the transport cost. So, and you should think that mu is, for instance, the location of a producer of a good, let's say the location of breweries, and nu is the location, is the distribution of the locations of consumers, let's say the pubs. And then each product X has to be brought to the consumer. F is this transport map, which says I bring this good from the brewery to this consumer. And I want to find a transport map such that the push forward of a distribution of a consumer, a producer is the distribution of consumers, so that this really matches. And I want to minimize the transport distance, measured in LP. Okay, you can do that. The problem is, however, that in some cases you will not find at all a transport map. Yeah, for instance, if there is only one brewery and two pubs, should it transport the beer to Bochum or to Dortmund? And then, at least mathematically, you are lost. Of course, here a majority would know how to solve this, but mathematically, this is not really a very, very good problem. Yeah. Sometimes it has no element in this minimizing class. The minimizer perhaps it's not a closed problem and so on. And fortunately, there is a relaxed formulation, which originally was not really thought to be a relaxation of that, but it's a relaxed formulation, as it turns out. Namely, the formulation of Kantorowicz asked now for the set of all couplings of mu and nu. And again, here is your distribution of producers, here's your distribution of consumers. And now you look on a measure on the product space, such that if you project this measure on the x-axis, you have a distribution of the producers. If you project it to the y-axis, you have a distribution of the consumers. And one possible candidate, of course, is the product measure. And you choose this Q in such a way that this is minimal. And of course, this product measure is not really very good, because as I already mentioned in this student interviews here, it would mean that each producer sends some of his goods to each consumer, according to the world contribution to whatever the market. A much better solution would be, with this same marginals, would be this product measure. And indeed, this is not an artifact. It turns out that in all typical cases, the optimal measure sits on a low-dimensional set. It sits on the graph of a function. And so, which means it is a Morse problem. So in all typical cases, indeed, this Kantorowicz problem leads to also to a solution of a Morse problem. Here the advantage is, first of all, you always find at least one Q, namely for product measure. And secondly, if this is a lower semi-continuous function in the space of probability measure, so you have a minimizer. Compactness and so on. So this is much nicer. And typical cases mean the distribution of producers is absolutely continuous. And then you have that Kantorowicz problem and Morse problem are the same. This goes back to various contributions, including Rüschendorf and Prenier. And so, as I mentioned here, Kantorowicz problem leads to the same as Morse problem, and we have a unique coupling of these probability measures. We have a unique transport map, and the transport map is given as the gradient of a convex function. And in dimension 1, you all know that, at least all who attended a course in probability theory or who gave a course in probability theory, namely, this refers to the fact that every probability measure can be represented as the push forward of a uniform distribution on CO1 in terms of its inverse distribution function, which again is the gradient of a convex function since it's increasing. And this is the higher dimensional version of this representation of a one-dimensional case. And in this sense, every probability measure can be represented uniquely by a convex function, which seemed to be a much low-dimensional, much easier space than the class of probability measure. This is a very nice and interesting result, and it allows us to give a good interpretation of the geometry of optimal transport. Now, if you think that our underlying space is a Riemannian manifold, maybe again this is a little bit sketchy. You don't have to really understand this part because we do not use it later on. But just for understanding it, we before considered Euclidean spaces and optimal transport. Now we pass to the Riemannian. We have almost the same results, namely given a measure which is absolutely continuous, there exists a transport map, and this transport map transports this mass to the target measure. And what we can do is we can transport this with the exponential map, but we can stop this exponential map, or we can smuggle in a parameter t here, and then we can stop the transport in between. We have a probability measure here and one there, and we want to transport this to that measure, and we can follow the trajectories which the particle x takes from its producing place to the consuming place. And if we stop everything at time t, then we have this measure mu t, and it turns out that this mu t is as a family in T, constitutes the geodesic in the space of probability measures, connecting mu0 and mu1. So abstractly, the space of probability measures has an infinite dimensional remaining structure. The tangent space is the closure of a gradient of C-convex functions, if you like, and the exponential map is just the exponentiation of this explicit function and using this to push forward the initial measure. Okay, this might look a little bit too cumbersome. As I mentioned, it's not really needed for the rest, and we therefore switch to an even more general situation. This requires that things get easier if you do it more general. So we now consider metric spaces, just x with a distance function. We define the Kantorowicz-Wasserstein distance, as I already indicated before. So given two probability measure, you ask for probability measures on the product space, which have the given measures as marginals, and with this measure you integrate out the distance square function. So it's the integral of a distance square with respect to a coupling, and then you minimize over all couplings. By compactness, indeed, there is a minimizer, but this is not relevant. This space of probability measure with this distance function, it turns out that this is a metric. You can prove triangle inequality. This is the only thing you have to prove. This is a metric space, and indeed, this is again complete separable space. If underlying space is complete and separable, if underlying space is compact, or if it's a length space, then the same is true for the Wasserstein space. And if underlying space is non-negatively curved, the same is also true for the Wasserstein space. Other curvature conditions are wrong. But this non-negatively curved condition carries over through all these integration procedures and so on. Okay, and now what is our definition of lower Ricci curvature bound? The definition which Lott, Villani, and I propose is that a space should be called non-negatively Ricci curved if a Boltzmann entropy is convex. Boltzmann entropy is this function. It's a function on the space of probability measures. It's the entropy with respect to the reference measure. Yeah, our setting is now a triple: metric, space, metric, and distance. Space, metric, and measure. And we use the measure to define the Boltzmann entropy, and we use the distance to define the Wasserstein distance. And this is regarded now as a function on the space of probability measures, and abstractly we say a function on whatever metric space is convex if it's convex along all geodesics in this space. And or weakly convex would mean that it's convex in the sense that between any pair of points you will find a connecting geodesic such that it's convex along this connecting geodesic. This is the more precise definition, but yeah, roughly speaking it means it's convex along every geodesic. Convexity, you drop this last term. K-convexity means there's a quadratic correction term with K, and this gives the K-convexity, which says roughly that the second derivative is larger than K. So this is the definition of non-negative Ricci curvature. We use the two ingredients, the measure here and the distance there. And we do not use any differentiability to define that. And then okay, there are two parameters, k and n. Now we discuss the second, because it's called curvature dimension. The second, the role of a second parameter for dimension is most easily discussed if we set the curvature 0. Then this condition means that the Shannon entropy, the Rheinische entropy is convex, and the Rheinische entropy is now this object where the rho log rho is replaced by a rho to a small power. And okay, let me try to indicate in one example why this might be a natural object. If you calculate the Rheinische entropy to the uniform distribution on a set A, a simple calculation shows that this is the negative of the nth root of a volume. The nth root of a volume, and now the negative nth root of a volume should be convex, so the nth root of a volume should be concave. And this reminds us that non-negative sectional curvature means that the distance function is concave. And roughly speaking, what we discuss here, the nth root of a volume is of a physical dimension of a distance, or other way around, the nth root of a volume is a mean value of a side length. And the concavity here required in each coordinate is now replaced by a concavity of a mean value of a side length. And in this cartoon, we try to indicate that in some coordinates it might be convex, but it's more concave. It could have some negative section curvature, but in average, the section curvature should be positive, in average with respect to the dimensions. Okay, so this is roughly speaking what comes out, but making this to a definition, of course, is not really a good idea. The good idea was to use the concept of optimal transport. Why was this a good idea? Okay, before I do that, I have to tell you a little bit more of a Kn condition where both parameters are non-trivial, but this is an ugly condition. We see again here the Rheinische entropy, but then complicated coefficients instead of t and 1 minus t. But you should not spend too much time on reading that. What is relevant is that in the Riemannian case, this is really an equivalent characterization of Ricci bounded from below by k and dimension bounded above from n. And besides the Riemannian manifolds, it also applies to weighted Riemannian spaces, to Ricci limit spaces in the sense of Giger-Kolting, to Alexandrov spaces, Finsler spaces. If you modify the concept a little bit, that your measure or your distance is allowed to take values infinite on large sets, then this also applies to the Wiener space and gives you curvature +1 for the Wiener space, configuration spaces. And there's a huge toolbox of constructions, how you can construct new spaces out of given ones, passing to limits, products, cones, suspensions, warp products. And this makes it to a very rich family. In particular, warp products allow to construct really huge classes of spaces which are not studied so far. What can you prove with that? If you have a curvature dimension condition with parameters k and n, and if k is positive, you have this diameter bound, which is similar to the diameter bound in Alexandrov geometry. Yeah? You need positive curvature, of course, but it's sharp, and it's an equality in the case of a sphere. You have a volume growth estimate, Bishop-Gromov, again with sharp quantities. So this is the volume of a sphere with small radius, volume of a sphere with large radius, and it's bounded from below by the corresponding quantities from the model spaces. Again, with sharp constants. What was surprising is that also in the case n equal infinity, there's a new volume growth exponent, volume growth estimate, and in all finite dimensional volume grows at most exponentially in R. And here we have a volume growth which is e to the r squared, which was not observed before, which is typical for infinite dimension cases. Most important are the stability result. The curvature dimension condition is stable under convergence. This was in some sense really the missing piece in all this Giga Colding stuff, the stability and the compactness result. And stability and compactness, of course, requires that you have a certain topology or metric, and you can use what is called measured Gromov-Hausdorff convergence, which is not really the exact concept, but okay, it fits to that. Or you can define a transportation distance between two metric measure spaces. It's not the same distance which we have seen before. Before I have shown you a distance which makes this space of spaces to be non-negatively curved. This is now a transportation distance where you use couplings of the measures and coupling of the distances. And this is essentially equivalent to measured Gromov-Hausdorff. But intuitively, this really means that things behave as you think intuitively. You have two metric measure spaces, you embed them into a big space, and you want that the measures converge weakly and the spaces converge in Gromov-Hausdorff sense. It's not exactly that, but roughly that. A big challenge was to prove local to global, and this was easy in the two cases where curvature dimension simplifies, namely curvature 0 or dimension infinite. This was clear from the very beginning. Then there was a step in between, which I worked with Bakry. But the original problem was open for 15 years to prove that the curvature dimension condition with general parameters K and N has the local to global property. And only a few years ago, Cavaletti and Millman, using this strong new technique of needle decomposition and the localization technique of Cavaletti-Mondino, could prove the local to global property. And of course, this is an important piece if we want to regard this curvature dimension as a curvature concept. Curvature means it should be defined locally. But up here, all our definitions are global definitions. Yeah? We say, I have a probability measure here, I have one fair, I transport the mass from A to B. But you can localize it, and it still gives you the same. Now, let us pass to the analytic aspect of metric measure space. Can we do something like heat equation on these spaces? Can we define Brownian motion? Can we speak of spectral calculus? Can we estimate eigenvalues and so forth? This requires that we have a Laplacian or that we have a Dirichlet energy. Okay, or heat equation. Let me start with a heat equation. We can define the heat equation of a heat flow for functions or for measures in two ways. One way, this is more of a traditional way, is to think that the heat equation is the gradient flow of an energy in L2 space. L2 space is well defined, it's a linear space. Energy is a little bit complicated if you're on a metric measure space. Intuitively, you want that it's something like integral of grad u squared, but what is a gradient in a metric measure space? Indeed, there is a definition which goes back to the Finnish school of analysis, the minimal weak upper gradient. Weak upper gradient is a concept which I could explain in one line. Upper gradient and minimal upper gradient would be easy. Weak means some condition holds for almost every curve. And with almost every curve means I would have to tell you a notion of a capacity on curves, which is quite lengthy. But okay, there is a notion of minimal weak upper gradient, which is defined pointwise and which gives a definition of its energy. There's another definition which is more naive and more straightforward. Namely, you say, okay, I do not have a gradient, but I know what is the local Lipschitz constant. If I have a distance function, I can define the local Lipschitz constant. I square it, I integrate out the initial point, and that's it. This is my answer. But in functional analysis, if you want to perform a reasonable calculus, you need that your energy function is lower semi-continuous. Otherwise, you are lost. There is no semigroup, nothing like that. but what do you do if you have a non-negative function which should be lower semi-continuous, but which is not necessarily? You make it lower semi-continuous. That's it. And what does it mean, make it lower semi-continuous? You just pass to Villani. If you have a function of a real line, which is not lower semi-continuous, take Villani, then it's lower semi-continuous. And this is what is made here. So this is, first of all, our naive ansatz for the energy functional, and then we want that this is lower semi-continuous in L2 space. And therefore, we have to take the lim-inf in L2 space. But there is a warning. Taking a lim-inf in L2 space is really a very horrible procedure. A posteriori, you know nothing, because you do not mostly you do not really know how the lim-inf changes this object. But it's well defined, and you have something, and the whole thing then is called Giga energy nowadays, and it was pushed forward very much by the Italian school, Ambrosio, Chile, and Savary, and they proved very deep and important results. They brought together the Giga ansatz and the Finnish ansatz, and all ways to define the energy have been identified more or less. There's another way to the heat equation, which goes back to Felix Otto, or Jordan Kinderlehrer Otto, which says we can regard the heat equation also as a gradient flow of entropy in Wasserstein space. Now we regard the heat equation as a flow of measures. Here we regard it as a flow of functions, but if you think that this flow of measures always produce measures which are absolutely continuous, then we can switch between measures and functions. So now we think of a flow of measures, and it's regarded as a gradient flow of entropy. Just for non-expert, what does it mean, gradient flow? This is a curve which tries to minimize this function as fast as possible, and as fast as possible, of course, means it has to obey the distance function in this space. It cannot jump to zero. It flows according to the distance function here, and here the distance function is the L2 distance, here's the Wasserstein distance. And as I mentioned, the group Ambrosio, Chile, Savary, in number of papers, altogether certainly more than 1,000 pages, have proven then in about 10 years ago that both approaches always coincide whenever the second approach makes sense. And the second approach, if you want to speak of a gradient flow, you have to have a lower semi-convex function. So here the problem was, first of all, the definition of the energy, but then nothing, because L2 is a nice space, you have convexity, you have gradient flow, you are done. Here it's a little bit more sophisticated. The definition of the entropy is for free, it does not require anything, but the existence of gradient flow is not so clear. You need at least semi-convexity, and semi-convexity is exactly our curvature dimension condition. It's the semi-convexity of the entropy. And just to indicate that this was then a result of a long development, I have listed here a number of results, and actually only some of these results are covered by this general result. Many of these results then go beyond. For instance, in Heisenberg group, we don't have curvature dimension condition. On discrete spaces, we don't have that, and so on. So this meta theorem holds even in situations which are more general, where you don't have curvature condition. But of course, as a theorem, you need here the curvature condition, the semi-convexity of the entropy. But the equivalence of both approaches seems to go far beyond that. And what does this equivalence allow us? It allows us to switch between the Lagrangian picture and the Eulerian picture. The Eulerian picture is more coming from the PDE aspect. So let me say this is something like Bochner inequality, where you have a Laplacian and a gradient, and the Bochner inequality is essentially saying what happens if you commute the Laplacian with a gradient. And it turned out, and this is one of the deep results of Ambrosio, Chile, Savary, and also of work of Erba, Kowada, and myself, that this curvature dimension bound, which heuristically can be written as second derivative of an entropy minus 1 over n times gradient of entropy square is larger than k as a formulation in Wasserstein space that fits Lagrangian picture where we think of transport, of geodesics, of particles moving around, that this is equivalent to this PD inequality. And so this is then the inequality. You have a dynamic version, which is a gradient estimate, and here you have a dynamic version is the transport estimate. This is just to indicate a little bit how this Lagrangian picture, which I have focused so far, matches with an Eulerian picture, which actually was developed by Bakry and Emery already decades before, but not in this general setting, and of course not with stability result. The stability you can prove only in the Lagrangian picture, but we have an equivalence, a complete equivalence between these pictures. Okay, what can we prove as in the sense of estimates in geometric analysis? So I have listed here just a bunch of names which have been contributing to this numerous estimates. Maybe one of the most beautiful results is a spectral gap estimate. If we have curvature dimension condition with parameters k and n, we have a spectral gap, or Lichtenowitz inequality, where the spectral gap is larger than a number times k. K is the lower Ricci bound, and of course it should be positive, otherwise the condition is, the statement is void. And this is a result which makes sense both in finite and infinite dimensions. If n is infinite, this prefactor simply drops. If n is finite, it improves your result. And here I have listed some results which require finite dimension. We have Laplace comparison results in the sense that the Laplace of a distance function is bounded from below by the Laplace of a distance function for model space. Bochner inequality, Liao differential Harnack inequality, Gaussian heat kernel estimates, Sobolev inequalities, Giger, Buser, and so on. It's too much to list them up. And for many of them are counterparts which apply to dimension-independent or infinite-dimensional settings. This is the Log-Sobolev inequality, the Talagrat inequality, the Wang-Harnack inequality, Ledoux inequality. This is just to indicate which family of function inequalities. Now, some more specific results. Splitting theorem of Chile. This was one of the important challenges which had been posed to us by the community. Can you prove also the splitting theorem? Splitting theorem in Riemannian geometry says if you have non-negative curvature and a geodesic which goes infinite in both directions, then your whole space splits into this real line times another space, which has again curvature bound. If you find one curve going in both directions as a geodesic, and Chile could prove that, and he could prove that this space decomposes into a space which has n-1 dimension, and again non-negative Ricci curvature and the real line. And of course, then you want to iterate that. If you can iterate that, finally you end up with a 0-dimensional or 1-dimensional space. And Ketterer did the same thing for spherical suspension, whatever this is. He proved if a space with let's say curvature n-1 and n, so positive Ricci curvature, you have a diameter bound pi, and if this diameter bound is attained, then the space has a specific form. It's again kind of a product between a circle and the space. And with Erba, we could prove a new rigidity result, namely if you have these curvature conditions, and if a double integral of a cos of a distance function is non-positive, then n has to be an integer and your space is a sphere. So we liked that result very much. And counterpart of maximal diameter theorem is Opper's theorem, which is a kind of minimal spectral gap. So we have seen a spectral gap estimate, and if this is attained, again, the space splits into a circle and a base space. And there's a counterpart on infinite-dimensional spaces which gives a Gaussian splitting, which again is new. Now the last family of results concerns the regularity, and these are important breakthroughs by Mondino, Neighbor, and Pruitt-Simula, which essentially now say that such a space which has curvature bound and dimension bound and finite dimension is almost a Riemann manifold in a vague sense. Namely, if a space decomposes into a finite number of components plus a zero set, and each of its component is bi-Lipschitz equivalent to a subset of k-dimensional Euclidean space. The measures are absolutely continuous to the Hausdorff measure, and indeed only one of its components has positive mass. So the dimension cannot change along the space. So there is one dimension which has positive mass, and then of course the boundary might exist, which has zero mass, and where you have again a manifold structure with n-1 dimension. And there are further refined results, but essentially this says you have a very good control now of this structure if you have this finite dimensional situation. You need RCD-Kn curvature dimension with a finite dimension parameter. And if a dimension parameter is 2, then it's indeed Alexander space, as it should be, but you have to prove it. Okay, now what is going on? What are modifications of this concept? I can talk a little bit on variable and distribution valued Ricci bounds on time-dependent spaces. I will do that in a minute. I won't go in details concerning discrete metric measure spaces. I mentioned this in the very beginning, that this condition of this possible definition of Ricci curvature in terms of this contraction rate of heat flows can be used to define contraction rates of Markov chains, and then regard this as a discrete Ricci curvature. A modification of this discrete Ricci curvature indeed is used to define Ricci bounds in a non-commutative setting, which is an interesting research direction where important contributions had been proposed by Karl Marx, Hornshaw, and Wirth. It's also interesting to look on this formalism where the dimensional parameter is negative. So for us, this is just a parameter. Yeah? It's just a real number. So far, it was always larger than 1. But it's a parameter in functional inequalities. And there's interesting work where this is a negative parameter. So this leads to quite different objects. There's also work, not much, but there's an attempt to apply this to directly boundary conditions and doubling of measure spaces, but this is only few contributions to that. I will go a little bit to point 1 and 2. Variable Ricci bounds, what does this mean? Okay, instead of a constant, now you have a function, which defines your lower Ricci curvature bound. And what you would expect, instead of this gradient estimate with a constant, you obtain a gradient estimate with a Feynman-Katz formula, where this operator heat semicube and e to the minus kt is put together to make a Schrödinger semicube. And this is then the gradient estimate for variable curvature bounds. And okay, if you look on this, you can easily believe that this k also could be singular again, not just a smooth function, but maybe a Carter class function. And this is one of the interesting research directions of Caron, Mondello, and De Vautrose, which produced an impressive number of results in geometric analysis, where they prove geometric functional inequalities under Ricci bounds which are in Carter class. And another interesting direction was by Guinnessy, von Rheinische, and Brown, which apply this to the so-called molecule space. If you apply the whole thing to Neumann boundary condition, you see it's not only for Ricci curvature in the interior, it's also bound for the second fundamental form on the boundary, which is integrated against the local time of the boundary. And if an abstract way you bring together these two terms, it means you end up with a distributional valued Ricci bound where K with a volume measure in the interior is augmented by the bound on the second fundamental form multiplied with a surface measure. And then you can deal Ricci bounds which are in negative Sobolev space. But okay, I do not want to go in more details. And one other direction which is very interesting are time-dependent spaces. There are three directions which I want to mention. There is one direction which goes towards super Ricci flows. This is the parabolic analog to spaces with non-negative Ricci. And so this, of course, is motivated by the work of Hamilton and Perelman, McCann, Topping, Lott, and many others. I will show you one result as the last result. And the super Ricci flow stuff, which is in some sense very nice and almost self-contained, this has to be augmented by something which allows you to characterize super Ricci flows, which are characterized by inequalities, with a corresponding upper inequality. And this asks for something like synthetic upper Ricci bounds, which is a very delicate object. And last but not least, there is a very strong research direction right now in to apply Ricci bounds in time-like directions on Lorentzian manifolds. So instead of going from the elliptic to the parabolic or to the hyperbolic situation, and you apply that in order to study Einstein equation in general relativity. And there is a huge research activity around McCann, Mondino, Cavaletti, and you see here this paper of 10 or whatever people. And in Vienna, they recently got a research grant, about 10 million euro just for research in these directions. Let me point out the last result concerning this first point here, namely a result of Eva Kopfer and myself, where we characterize super Ricci flow. And let me perhaps first start here. What is a super Ricci flow in Riemannian setting? If you have a time-dependent family of Riemannian metrics, you say that this family is a super Ricci flow if a Ricci curvature plus 1/2 of a time derivative of a metric tensor is non-negative. So in this sense, this is the parabolic counterpart to non-negative Ricci curvature. It's a parabolic equation because the Ricci is roughly something like a Laplacian. And so you have Laplacian in terms of a metric coordinate. So you have this super Ricci flow. Ricci flow would be with equality here. And now we have a metric measure space characterization. We have a version of a convexity of entropy, which is of course then much more complicated. In this shorthand notation, this means, let's say if the time goes in this direction, and then in a given time slice, I look on an optimal transport, and I look on the slope of this entropy on the left-hand side, on the right-hand side, and the difference should be bounded by the change of a distance function. And the slope, which is here, corresponds to the Ricci, and this corresponds to the time derivative. And maybe the most interesting then is we look on this characterization in terms of Brownian motion. This sequence of spaces evolving in this time direction is a super Ricci flow if and only if whenever I start whenever I choose 2 points, x and y, I can couple them in such a way that if they run downward, they never increase the distance. So the spaces evolve in this direction, and the Brownian motion go downward, and going downward, they never increase distances. If this is the case, then I have a super Ricci flow. And gradient estimate, again, and there is this shorthand notation that the gamma 2 operator of Bakry and Emery, which is defined that way, is dominated from below by 1/2 of a time derivative of a gamma 1 operator. And, oh, sorry, I'm over time. Thank you for your attention.